Hello everybody. Today I'm going to explain and demonstrate what is a frequency response as far as sound is concerned. So frequency response by definition is a quantitative measure of the output spectrum of a system or a device in response to a stimulus. Simply put, it is a measure of how well a physical system is able to reproduce the input without altering it much. So as far as the audio is concerned, what is frequency response of a speaker, if you may ask? The frequency response of a speaker is a measure of how well the speakers are able to reproduce the digital sound in a live fashion without, changing much of the features, without altering the sound properties such as the frequency and the amplitude. To understand how well a system can reproduce this input without altering the frequency and the amplitude, we need to study and plot something called as a frequency response plot. Now, estimating the frequency response for a physical system generally involves exciting the system with an input signal and then measuring both the input and output and then calculating the frequency response. It is very important to note that the frequency content of the input signal must cover the frequency range of interest of a physical system. Otherwise, you may get an error if you're outside the interested frequency range. For example, if your range of interest is within the human hearing range, such as 20 Hz or 20 kHz, you must ensure that you are playing the input signal within this range, that is from 20 Hz to 20 kHz, and you're not anywhere short. Alright, there are different ways to determine the frequency response of a system. There are three ways. The first is applying impulse to a system, meaning exciting the system by striking it and then measuring its response. Now, its response can be measured by two ways. You can connect an accelerometer and measure the vibration, the X, Y, and Z accelerations, or you can put a microphone in front of it and then, capture the sound emitted by the system. And the second method is sweeping a constant amplitude pure tone, meaning, playing a sine wave right from 20 Hz to 20 kHz and then capturing the response. And the third one is playing a signal with wide frequency spectrum, such as white noise or pink noise. As far as audio is concerned, we use a second method, which is simple and easy. Alright, so this is a frequency response, for example. Now, how was this frequency response even plotted? For that, let's perform an experiment. Consider a speaker whose frequency response is to be determined. Now, let's play a sine sweep file through the speaker. So the file will be sweeping the sine wave from 20 Hz to 20 kHz, which is within the human hearing range. So the sine wave file swept from 20 Hz to 20 kHz is the input file, and the sound coming out of the speaker is the output. So what we're trying to do really here is to measure how well the speaker or the output is able to reproduce the input or the original sine wave. So if the output is exactly same as the input, then the deviation is 0 and you'd be observing a flat line in this graph. But there may be regions where the output is not able to reproduce the input. Now those are the deviations, and the deviations can be positive or negative. So let's consider this example. So in this graph, you'd be observing, the y-axis is the deviation and the x-axis is the frequency in hertz. So in this graph, we're observing that from 200 hertz to approximately 2000 hertz, the graph is, approximately flat. So, it has a flat frequency response in this bandwidth, which means a speaker will exactly reproduce a sound if it's falling within this range. But below this frequency, below 200 hertz and above 2000 hertz, the speaker is not able to reproduce the input appropriately. Below 200 and below 100, the deviation is really large. It's going negative, whereas above 3000, it's going positive. So this is like an average frequency response where some portions are flat, there are deviations in some places. Now let's look at a flat frequency response, something that an audiophile would love to have. Alright, this is an example of a flat frequency response. As you can observe the graph is just a straight line. The deviation is zero, except in the lower bass region from 20 hertz, 30 hertz, it's going down. Otherwise, it's just flat. So what does this mean? It means that the output is exactly same as the input, or the physical device will exactly reproduce the intended sound without any deviation, without any frequency addition, amplitude addition, or deletion. So it's going to reproduce the sound as is. A very good application is in hi-fi audio, such as stereo headphones, high-end stereo headphones, and studio monitors. Because the mixing engineers need to really know the sound exactly as it is, so that the mix goes well. All right, so there is another thing. There is an ideal frequency response. So that is just like a straight line, like there's not even a single curve, but that's ideal. You can't achieve that due to limitations in the physical systems. The speaker has to be manufactured, so there are lots of problems as far as that is concerned. Let's take a look at why the frequency response cannot be exactly flat, and even to achieve this frequency response, you need to do a lot of engineering. So let's take a look at what are the practicalities, what are the difficulties that you gotta face in order to get such a response. Every manufacturer would ideally dream of having a flat frequency response for his audio products, but there are lots of practical difficulties in achieving a flat frequency response. This is because of physical components. For example, a product like speaker has lots of physical and mechanical and electrical components. For example, the driver and the circuits. So every single component has to have a flat frequency response so that the final sound has a flat frequency response. So if each and every component offers a flat frequency response, they'll not distort the sound in any way. They'll not boost or cut any frequencies, so that the final output is flat. But if any component in the chain has a non-flat frequency response, so that's going to show up in the final sound by boosting or cutting down certain frequencies. Alright, this is a comparison of different frequency responses. So there are three graphs here. There's yellow, green, and red. So the green one is the ideal frequency response. I mean, it's insanely ideal case because it's just flat. So there's not even a single curve, like at the lower and the higher end of the spectrum. But a real life case which can be considered ideal is the yellow curve. I mean, so it is going down at the edge of human hearing at 20 hertz and 20 kilohertz. I mean, it is popping up a little bit at the base and the high frequency regions, but still it's admissible because the variation is gradual. It's not sudden, unlike the red curve. I mean, if you observe the red curve, the change, the fluctuation is rapid. I mean, it's not gradual, so it might affect the timbre, the sound quality of whatever it's gonna play. Alright, a flat frequency response, although difficult to achieve and extremely useful in music, is not always necessary in all cases. For example, in case of a telephone, you don't need a flat frequency response. Even this response in this example is good enough, excellent for a telephone. That's right, because here, as you can observe, the frequency response is flat from 2000 to approximately 2500 hertz, and that's good enough because the human voice is gonna be in that range, and you're not gonna be using treble or bass in a telephone, so there is no need to have any flat frequency response in the bass or the treble region, because the purpose is pretty much solved if you have a flat frequency response in the mid region from 200 to 2000 hertz, and you can have good speech intelligibility in that region. So yeah, so it's not always necessary to get a really flat frequency response. You need a frequency response based on the application, and if the job is getting done with a good enough frequency response, you should go ahead with that. Alright, there is a way to determine if an equipment has a flat frequency response or not by just studying the spectrograph. So what we do is first we use the original digital signal and plot the spectrograph. So this spectrograph is a spectrograph of a digital signal. And then we play the digital signal using a speaker and plot the spectrograph again. Now the spectrograph of the speaker, is exactly the same as the digital spectrograph. It means the speaker has a flat frequency response because it has reproduced the sound as is. But in case if the spectrograph of the speaker is not same as the digital spectrograph, if it has some boosts or cuts, it's a clear indication that the speaker does not have the flat frequency response. Alright, now what I'm going to do is I'm going to play the original sound signal, and this is the original spectrograph. Let's see. Alright, so now you heard a melody track, and this is the spectrograph. Now I'll be playing the same melody track through a speaker, and I'll be displaying the spectrograph here. Alright, this is the spectrograph of the sound, same melody track played through a speaker, and this is how it sounds like. When I heard the sound, I felt that the sound is not exactly the same as the original digital signal. I also heard a lot of bass, which which is reflected in the spectrograph. Alright, so what we're going to do is we're going to compare both the spectrographs and study them carefully and conclude if the speaker, if it has really a flat frequency response or not. Alright, this is a comparison of the spectrograph of the original digital signal and the signal played through a speaker. When we compare both the spectrographs, we observe that the spectrograph of a speaker is not reproducing the original spectrograph because it does have a peak in the lower bass region around 50 Hz, and then it does have the fundamental frequency around 300 Hz, which is present here in the original spectrum. And the original spectrum also has a bunch of trailing harmonics all the way up to 9000 Hz, which is kind of reflected here in the spectrograph of a speaker, although not accurately because there are certain dips and troughs here, whereas here it's just gradually decreasing in amplitude. So overall, yeah, the speaker doesn't do a great job in reproducing the exact sound, and hence the speaker does not have a flat frequency response. Well, it is possible to achieve a flat frequency response. It's just that you got to spend a fortune in order to achieve that. As I mentioned earlier, every single component in the device contributes to that. So if you really want a flat frequency response, you got to ensure that each and every component has a flat frequency response. Alright, thank you for watching this video. I hope you enjoyed it. If you have any questions or comments, hit the comments. I'll be sure to respond. Alright, thanks a lot. Have a great day.